All right, here we have the notes for section 4, the basics of multiplication rules. So this is just your notation, P and A and B. So event A occurs in the first trial, and event B occurs in the second trial. So with the bar symbol, that means B occurs after you've assumed that A has occurred. So B after A. All right, so here you've got the formal multiplication rule. So how the math works, the probability of both A and B occurring is the probability of A times the probability that B occurs, given that A has already happened. That's the mathy version. Intuitive here. To find the probability that event A occurs and event B occurs, you multiply the two probabilities together. But you have to take into account that B must take into account that A has already occurred. That refers to this stuff being independent versus dependent. So two events A and B are independent if the occurrences does not affect the probability of the other one. So like rolling a die, what you get on one die does not affect what you get on the second. Coin flips are independent. If A and B are not independent, they're said to be dependent, which means that one affects the other one. So if you're drawing cards from a deck without replacing them, those are dependent events. You're changing the number of cards, which comes down here to sampling methods. Sampling with replacement, so that means you draw something, look at it, and then put it back. So that's with replacement, which means the probability won't change, it'll be independent. Dependent is if you do not replace the item you've drawn. So you're pulling people out of the class, there's 20 kids in the class, the probability of any one person being selected is 1 out of 20, but if you don't replace them back into the classroom, now the probability is 1 out of 19, so on and so forth. Okay, so example 1 here. Should put a little space there. Using only the 50 test results from the subject to take drugs from section 3, example 1 is shown below. So we had 44 positive tests, 6 negative tests. If 2 of the subjects are randomly selected with replacement, find the probability the first person will have a positive result, the second person will have a negative result. So to get the positive result, that's 44 out of 50. And then I put the person back. So now the negative test result would be 60 out of 50. And then I just need to multiply those two things together. So I'm going to calculator, 44 over 50 times 6 over 50. And that comes out to be 66 out of 625, which is, as a decimal, 0.106. Now down here, we're going to do it without replacement. So the first person, still 44 out of 50. But now when I go to draw my second person, 6 negative test results, but now there's only 49 people to select from. So this is going to make my answer a little bit different. So 44 over 50 times 6 over 49. So this is 132 out of 1225, which as a decimal, not totally different, but not exactly the same. So there's your value. Okay, so for example 2, talk about, whoops, can't see it. There it goes. We have 102 scales were defective out of the 810. So if 2 out of the 810 scales are selected with replacement, that they're both defective. So now to this one, so that's drawing the first scale, and then I put it back, so I still have 102 out of 810 each time. So this is the same thing as 102 out of 810 squared. So 10, out of 810 squared is 289 over 18225, which as a decimal is 0.016. Okay, so down here, we're doing it without replacement. So 102 out of 810 to draw the first scale. Now I'll draw the second scale. It's going to be out of 809 because I have one fewer scale to choose from, but I also have one fewer defective to choose from. So I have to be careful about it. So 102 out of 810 times 101 out of 809. Oh, this one doesn't even give me a fraction. 0.016. So it's almost the same. If I carry more decimals, they'd be more obviously different, but this one is slightly more than that one. Okay, down here, we're going to draw 5 out of a 10,000. We know that 1,259 are defective. We're going to draw 5 randomly. Now, this is an example of shortcutting the problem. So if you notice, these are almost, these guys are almost exactly the same. The thing is, if your sample population is small, less than 1/5 of this, or sorry, not less than 1/5, less than 5% of this number, you can shortcut the problem. So this number is only, well, it's small compared to this guy. So instead of doing each individual one, I can just take the probability of 1 and raise it to the 5th. Now this trick only works if this number is small compared to that number. So 1259 over 10,000, all raised to the 5th, is itty bitty number, 0.000003. So it's very, very unlikely that you would select 5 at random. All right, so example 3. So we're going to select random people from the class. Actually, it doesn't matter. This probably always works out the same. Doesn't matter how many people. By assuming birthdays occur on the days of the week with equal frequency, which means Mondays are just as likely as Tuesdays, as Thursdays, so on and so forth. Find the probability that 2 people are born on the same day of the week. Now, there's a trick to this problem, because the first person can be born on any of the 7 days. So the first person can be born on a Monday, doesn't matter. For the second person to match them, they have to be born on one specific day of the week. So the probability of 2 people being born on the same day is 1 in 7. Now, if you want to be specific about it and say they're both born on a Monday, that changes it, because then it's the first person has to be born. They have a 1 out of 7 chance being born on Monday. So does the second person. So if you are specific about the day of the week, it makes the number much, much less. So this is, it's a decimal 0.020, and 1/7 as a decimal is 143. So if you say any day of the week, you have about a 14% chance of the people being born on the same day. If you say specifically on a given day, it's much smaller. Alrighty, which brings us, I believe, to the last page. Yep. Okay, so example 4, it says, we're talking about the gender selection technique. 20 couples give birth to 20 babies, and all 20 babies are girls. If we're to assume that XOR has no effect, what's the probability of that actually happening? So the trick to this is the likelihood of getting a girl, there's only, we'll call it 1/2. If we're doing this 20 times, instead of writing out 1/2 times 1/2 times 1/2 times 1/2, so on and so forth, we can just raise it to the 20th because we're reading all 20 kids. So 1/2 to the 20th. It's a very, very small number, 0.12345 and then 95. So this is a vanishingly small probability. So this says this is unlikely to have happened. This is very, very, very small. So it's unlikely that you would have, out of 20 births, all 20 are girls. So then it gives you the actual numbers here. So 945 babies born, 879 were girls. The probability of these events occurring by random chance were 0+. Now this notation means there is a chance, it's just a positive number super close to 0. So there is a very, very small chance, but it might as well just be 0. So this probability of 0+ provides strong evidence to support that it is effective, yes. Because if it actually happened, the likelihood of this happening is so small by chance that something else had to have happened. So if something has a very low probability but actually did happen, you can probably say that some other item had an effect. Okay, and then last one. So probably of 1 failing. So that's the likelihood that, so that's the likelihood it fails. So the likelihood of it working would be that. And then 3 independent systems. So what I need to do is figure out the likelihood that all 3 fail, and then subtract that from 1, because I want the opposite thing to happen. So 1 minus 0.002 cubed is 0.99999. 1, 2, 3, 4, 5, 6, 7, 8 nines. So there's 5, 6, 7, 8. So it's very, very likely you'll get through your flight safely. And that is the end of the section.